main results of the presentation I gave the last lecture on the Dirac method for Dirac algebraic method for solving a hydrogen atom. My mind is elsewhere this morning. The Dirac algebraic method for solving a harmonic oscillator. I think you're probably familiar with most of this. The essential ingredients are the creation and annihilation operators. There are matrix elements with respect to the energy eigenstates. The expression of the Hamiltonian in terms of the creation and annihilation operators. We've also solved for the position and momentum in terms of the A's and A daggers, just the inversion of the definitions, which is also sometimes useful. All right. Now, I'd like to begin today with the subject of wave functions. In particular, let's talk about the ground state wave function. 0 is the ground state. And if I form the scalar product with the position eigencat x, we get what we consider to be the ground state wave function called psi 0 of x. The question is, what is psi 0 of x? Well, this follows easily from the fact that the annihilation operator acting in the ground state annihilates. It just gives you 0. The annihilation operator, however, is x plus ip over square root of 2. And if we put that in the wave function language, x plus ip goes over into x, of course, is let's put hats in this and emphasize these are operators. X goes into multiplication by x, p goes into minus I ddx. So, excuse me. So, as an operator, acting on the wave functions, this goes into x plus ddx. And therefore, the ground state wave function satisfies the differential equation that x plus ddx, acting on side 0 of x, is equal to 0. It's a simple differential equation, and it's easy to solve. And if you solve it and if you normalize the result, you find that psi 0 of x is 1 over pi to the 1/4 power times e to the minus x squared over 2. Pi stuff is the normalization. And this is the ground state wave function, which is, I guess you know, is a Gaussian function, the function of x. It's a Gaussian function centered at the origin. That's the ground state of the harmonic oscillator, psi 0 of x, here like this. Now, one of the things we're going to be interested in paying a lot of attention to today is expectation values of position and momentum, as well as dispersions, which are like expectation values of first moments. We'll also be interested in second moments, which are related to the dispersions. And in particular, if we compute these for the ground state, it's easy to show that the expectation value of x and the expectation value of momentum p are both equal to 0. This is for the ground state. And one can also show quite easily that the dispersion delta x is equal to the dispersion also in momentum p, which is 1 over the square root of 2. This means, obviously, the dispersions are equal, and it also means that the product of delta x times delta x times delta p is equal to 1/2. This is all in units and where h bar is equal to 1. So this would be h bar over 2 in ordinary units. And this is the minimum value of delta x and delta p, which are allowed by the uncertainty principle. So the result is the ground state harmonic oscillator is actually a minimum uncertainty wave packet. It's a Gaussian wave packet. All minimum uncertainty wave packets in terms of delta x and delta p have to be Gaussian, but this is a particular example of it. So that's an interesting conclusion also. While I'm talking about momentum, by the way, it's interesting to take the Fourier transform of psi 0 in order to obtain a momentum space wave function, phi 0 of p. That's straightforward. It leads to the same 1 over pi to the 1/4 normalization, and then it becomes e to the minus p squared over 2. The result is, as you see, that for the ground state anyway, the momentum space wave function has the same functional form as the configuration space wave function. This is an example of a wave function which goes into itself in a Fourier transform. All right. Now, so those are some basic facts about the ground state. Now, let's take a look at the excited states. Let's see. Maybe before I do that, let me just provide some motivation for where we're going here. The harmonic oscillator is a particularly useful system for exploring and understanding the correspondence with classical mechanics to understand how far it goes and what needs to be changed by going to quantum mechanics. It makes the relationship between the two particularly clear. And that's really going to be the main theme that we'll be following in the rest of the lecture today, is to understand the relation between classical and quantum mechanics. Here's just one thing to say, is that because this ground state of the harmonic oscillator has these dispersions, this is obviously related to the statistical nature of a quantum measurement. We can visualize the ground state of the harmonic oscillator in quasi-classical terms in the following way. If I plot the classical phase space x and p, then we can think of the ground state of the harmonic oscillator as a kind of blob or a distribution which is centered at the origin in phase space. It's centered at the origin because the expectation, the average values of x and p are 0, but on the other hand it has some spread around it because of non-zero dispersions. Spread, of course, is necessary by quantum mechanics because x and p don't commute, and so they can't be measured simultaneously with infinite precision. This blob that I've drawn here is not intended to be a rigorous representation of the ground state. It's really intended just for intuition, purposes of intuition, to give you an idea. It represents in some way the statistics of measurement that come out of the ground state wave function. One could make this more precise by going to the Wigner function, which was actually a part of last week's homework problem, but I won't go into that. We'll just use this for illustrative purposes. All right. Anyway, that's what the ground state looks like. Now, in thinking about the classical limit of the harmonic oscillator, or for that matter, any quantum problem, hydrogen atom, one is struck by the fact that in classical mechanics you have particles moving on orbits, and in quantum mechanics you've got these energy eigenfunctions. At least that's what people talk about most of the time. And an energy eigenfunction doesn't look at all like a particle moving in an orbit, and the question is why, what's the difference, and how do we understand this? Well, just for the case of the harmonic oscillator, let's shift attention down to the excited states, n. Say n is one of the excited states. Now let's consider the expectation values of position and momentum for the excited states, just to see, because expectation values of position and momentum are ordinary numbers, and they could be, they sort of look like classical quantities. So let's consider the expectation value of position, let's say, in an energy eigenstate. Then I'll put a hat on the x to emphasize that that's an operator. Similarly, we can do this for the momentum. Look at the average value of momentum in an energy eigenstate. By the way, my use of the hats here is that I tend to put hats on something to indicate that it's an operator when there's some danger of confusion between the operator and something else like an eigenvalue or a classical quantity. And I tend not to do it when there's no danger of confusion. That's the rule for the hats. For the time being. Well, in any case, these expectation values are easy to work out. The easiest way to do it is to write it in terms of A's and A daggers. And if you do that, you'll find quite easily that both these expectation values are 0. So, as far as expectation values are concerned, an energy eigenstate doesn't look at all like a classical particle in an orbit. If you have a classical harmonic oscillator and you give it some definite energy, it's going to swing back and forth with an amplitude. So the question is, where is that the classical time dependence in the quantum problem? It's not appearing here in energy eigenstates at all. In fact, energy eigenstates in quantum mechanics are what they call stationary states. That means the probability density in configuration space is independent of time. And so any expectation value you take of any operator is going to be independent of time in an energy eigenstate. Therefore, there is no time evolution at all. In particular, it stays 0 for all time. So it's disappointing if you're trying to make a connection with the classical orbit. Now, how can we understand this from an intuitive standpoint? Here's one way to do this. Let's go back to the classical problem. Here's the classical phase space like this. The orbit of the classical harmonic oscillator in phase space is a circle, like so. And let's say we've got some initial condition, call it x0, p0, which lies on this circle. Then the motion is a clockwise motion around the circle. It's classical motion. It's a clockwise motion around the circle. Let's suppose at a later time we've got x of t and p of t, another point in the circle. And then there's an angle in between. And that angle is actually equal to the time. Or if you want to restore ordinary units, then the time gets replaced by omega t. It's basically the phase angle of the harmonic oscillator. Roughly speaking, this looks like the hands of a clock. It even goes in the right direction, clockwise. All right. Now, So what this suggests is, okay, so the question is, why do we have expectation values of 0 for the energy eigenstate? Here's an intuitive way of understanding it. It's related to the time-energy uncertainty relation. It says that product of delta T delta E is equal to or greater than or equal to h bar over 2. This looks just like the delta X delta P uncertainty relation for position momentum. We haven't really talked about time-energy uncertainty relations yet, but we did talk about delta X and delta P. And in fact, the mathematics of deriving this is quite similar to what you use for the delta X delta P uncertainty relations. But the physical interpretation is different because T is not an operator, whereas X and P are. At least in the non-relativistic theory, that's how it is. And so the interpretation of this uncertainty relation actually depends on context, and it varies from one application to another. But in the present application, it means the following, is that if we have an energy eigenstate, then delta E is equal to 0 because in an energy eigenstate, the energy is exactly known. And in some sense, that means that delta T must be infinity. The sense in which that's true is that the idea is that instead of having something that's localized on a classical orbit in which you could tell the time if you thought of that as being 20 plus 2 o'clock, it's like, in order to make let me put it this way, to make a measurement of energy, precise measurement of energy so the energy is known exactly, the measurement process must extend over an infinite amount of time. That's another way of saying it. So if we look at the classical orbit, and we try to measure it over an infinite amount of time and blur our time clock, what happens is this particle gets smeared out over the entire orbit in a uniform manner. And if we do that, then even the classical average values of X and P are 0 because it averages to 0 over this oscillation. And that, in some sense, is the reason why we have these expectation values. And what it shows is that if we want to get some quantum object that looks like the classical motion, we can't use energy eigenstates. We've got to use a linear combination of energy eigenstates. Then those different terms in the expansion will have different time evolutions, and we'll get a non-trivial time evolution for the quantum state. So in particular, let's think about putting a minimum uncertainty wave packet, let's say, at some different position in phase space, some different expectation value besides 0 and 0, different from what we have for the ground state of the harmonic oscillator. All right, that's kind of an introduction to where I want to go for the rest of the lecture. I'm sorry I have to cover this up now, but that's the motivation. So now this takes me to the next topic that I want to tell you about, which is coherent states. First of all, a definition of a coherent state. In the context of mechanical oscillators like we're talking about now, a coherent state is a wave function which is, first of all, satisfies the fact that the dispersions of both position and momentum are equal and are equal to 1 over the square root of 2. And this means, in particular, that these are minimum uncertainty wave packets. This would be h bar over 2 if I restored ordinary units, but for simplicity, I'm going to get rid of the units by the physical constants by choice of units. It was I mentioned earlier, so it's called 1/2. All right, so coherent states are all minimum uncertainty wave packets, also, as far as the expectation value, position, and momentum are concerned, these are allowed to be anything. So in effect, the expectation values of X and P are parameters of the coherent state. And you can see in particular that the ground state of the harmonic oscillator is an example of a coherent state. It's one in which these expectation values are 0 and 0. And what we'd like to do then is to take this, in effect, take this ground state of the harmonic oscillator and thinking of it in phase space like this, we'd like to move it to other places in phase space to change these expectation values. Now, a nice way of doing that is to use translation operators. The translation operators that we introduced before are up at the top of the board. Excuse me for covering things again. But let me draw your attention to them. These are the translation operators that, as we defined them previously. The first line here is the definition of the translation operator. This is in one dimension, and the A here is the displacement for the translation. Don't confuse it with the annihilation operator. I'm sorry, it's the same symbol. The second line gives the effect of the translation operator of wave functions. And the third line gives the expression of the translation operator in terms of its generator, which is the momentum. I'm putting a hat here to indicate that's the momentum operator. The A here is an ordinary number, or C number, as Dirac would say. Multiplying P, it's really the displacement. Anyway, these are things we covered before. All right. Now, first question I'd like to address is how does the translation operator affect expectation values? So let's suppose we've got a state psi, and this has an expectation value I'll call x0, which is just psi sandwiched around x hat. And let's define a new state, call it psi prime, which is the translation operator T of A acting on psi. Now let's consider the expectation value of position operator with respect to the prime state. How does that change compared to the expectation value of the unprime state? Well, you can easily see by just substituting in here the definition of psi prime. This is the same thing as psi times T of A dagger times x hat times T of A times psi, like this. And so working out the answer is going to involve working out this conjugation relation of the position operator by means of the translation operator. So let's make a place over here where we're going to write the answer. T of A dagger, x hat T of A is equal to, and we'll fill this in just a moment. The easiest way to work out this conjugation relation is just use this second line here for what translation operators do for wave functions. Let me sketch it for you. You've got the wave function psi of x, so we want to apply T translation operator first, then multiplication by x, and then the inverse translation. So first of all, if I apply T of A to this goes over to psi of x minus A. If I then apply x hat, that's multiplication by x, so this goes over to x times psi of x minus A. If I then apply T of A, well, it's really T of A dagger, but these are unitary operators, so T of A dagger is T of A inverse, and that's the same with T of minus A. So let me write it this way, T of minus A, which is equal to T of A dagger. So here I use this middle rule here, except I change the sign of A, so it's x side of x plus A. So x here has to be replaced by x plus A. It goes into x plus A, multiplying 1 to psi of x. And this is the same thing as the operator x hat plus A, acting on the wave function psi, which is then evaluated at x. And so this sequence here shows you the effect of these three operators. And it shows you that the product of these three operators is the same as x hat plus A, right here. So there you are. There's the conjugation relation. And now if I take expectation values of both sides with respect to my initial state psi here, you can see this turns into the original expectation value, which is x0 plus A. So expectation values shift forward by A under a translation. Now this is pretty obvious because what the translation operator does to the wave function is it just pushes it down the x-axis, and so expectation values have to shift in the same way. Anyway, while we're at it, let's also look at momentum. What does T of A do to the momentum operator when we conjugate? And the answer is it doesn't do anything because T of A is a function of momentum. And so it commutes with it, so I can bring the T of A dagger past the P, where it cancels itself out, and we just get P. This is a position space translation operator, and it doesn't do anything to momentum, only the position variables. What does it do to dispersions, delta x and delta P? What happens to them? What does delta x go into under translation? Well, the dispersion, if you just think of statistics, it's a measure of the dispersion about the mean. It's really a difference between the mean and the actual value of x. It's the average of the square root of the difference, square root. It's the RMS difference. And the translation affects the x, but it also affects expectation values in the same way. And so the difference between the two cancels out when you do a translation. Translations don't affect dispersions. So delta x goes into delta x and delta p goes into delta p. Now, this is important because it means that if you have a minimum uncertainty wave packet, that the translation operator maintains the minimum uncertainty condition. That doesn't change at all. The only thing that changes is the expectation values. All right. And so, in particular, if we took the ground state of the harmonic oscillator in the space-based picture or image of it, so it's a blob here at the origin, here's the ground state 0, right there. And we apply a translation operator to it to get the state of T of A acting on the ground state 0. We can think of this as a blob here that's centered at position x equals A on the x-axis. In fact, it will just be that Gaussian wave function, it's just that Gaussian move down the x-axis is all it is. But let's look at it in phase space and think of it this way. So by doing this, using the T of A, you can change the expectation value of x. That's not quite what we wanted, though. We wanted to change the expectation value of both. Let's see, do I have it somewhere here? Of both position and momentum, because we were interested in starting some kind of wave packet out of an orbit here in an arbitrary initial x0 and p0. So to take care of the momentum translation, allow me now to introduce momentum translation operators. I think I can erase this part here to make this U table right next to the first one. Allow me to define, this is just a definition, I'll call it S of V. I use S just to make it a different letter from T, but this is a translation operator momentum. And this is defined, this definition of it, as e to the plus I V times x hat. V here is just a number, and it's going to be the momentum displacement, and the x hat is the operator. It sort of looks like this, except x and v have been swapped, and the minus sign has been introduced. So let's see what S of V does to wave functions. So first of all, if I take S of V and let it act on a wave function psi, and evaluate it at x, well, S of V is a function of the operator x hat, which is just multiplication by x on x-based wave functions. So this is just the same thing as e to the I dx times psi of x. Multiply psi of x by a position-dependent phase factor. What does this do to momentum space wave function? Let's call this psi prime of x. What does it do to momentum space wave functions? Let's write phi prime of p to be the momentum space wave function corresponding to psi prime of x. Well, that's the Fourier transform. It's integral dx over square root of 2 pi h bar. And then it's e to the minus I px. H bar is 1 here, so it's just 2 pi. Keep that one clear here. Cleaner, square root of 2 pi there. E to the minus I px. And then we need to multiply by psi prime of x, which is in the line above here. But I'll write e to the I dx times psi of x in place of psi prime of x, like this. Now you can see that this is the same as the Fourier transform of psi of x, except the parameter p has been replaced by p minus b. So this is the same thing as phi of p minus b, where phi is the Fourier transform of the original psi. And so the net effectiveness is that, I can write this way, is that S of v acting on a momentum space wave function as a function of p is equal to phi of p minus b. And notice how it's analogous to the position space translation operator. This, in effect, moves the momentum space wave function down the momentum axis by a displacement of v. Likewise, one can easily show that S of v acting on a momentum eigenstate p maps it into p plus b. And in this way, we have a parallel now between parallel set of formulas between position and momentum displacements. And so if we took our ground state wave function, which is a coherent state, and we displace it in x, we can then follow that by displacement in p. Let's call this S of v times T of A acting on 0. And you can think of it as a blob in phase space, which is centered on position coordinates AD, like this. Before I say more about this, let me go back to the question of expectation values, which I covered for the translation operators T of A over this panel. What does this new momentum space displacement operators, what does it do to expectation values? Well, it's the obvious analog of what T of A does. It works like this. I kind of like to put it over near this, so allow me to erase this. It works like this, is that S of B, dagger S of B, S of B dagger x hat S of B. So we conjugate the position operator by the momentum displacement. That just does nothing to it. The reason is that S of B is a function of x hat, so it commutes with it. And that's just like this formula here, with T of A and P. If we take S of B dagger and use it to conjugate the momentum operator, it goes into itself plus the displacement, which just indicates how momentum space expectation values are shifted forward. And then finally we have the definition. And then finally we have the effect on dispersions, delta x and delta p. Both of them go into themselves, that is to say they do not change, for the same reason that they did in the case of the x-space displacements. Yes, question?
Do the momentum and position translation operators commute?
No, the momentum and position translation operators do not commute, and that's in fact going to be my next point. Just one remark before I get to that is that by using these products of these operators, we can in effect take this ground state of a harmonic oscillator, which is an example of a coherent state, and move its expectation values around without changing the dispersions, and thus maintaining the minimum uncertainty wave packet property of these states. And so by doing this, we can create what we call coherent states with any expectation values of position and momentum that we wish. There's a two-parameter family of them that in fact cover all of phase space. However, because of this point that was raised here a minute ago, there is an issue we need to deal with, which is that getting to this point A, B in phase space, we first went in the x direction and then in the p direction. What if we went the other direction, applied momentum translation operators first and then position operators second? Would we get the same answer? And the answer is no, because these operators, T of A and S of B, don't commute with each other. That's no surprise because they're exponentials of operators, namely P hat and X hat, that don't commute. So there's a difference between these two paths in getting there. It turns out the difference between the two paths is only a phase factor. And some people would say that's not very important. But nevertheless, I'm going to devote some attention to giving a more symmetrical way of getting to the final location that gets around this, that deals with this phase factor in a manner which is symmetrical under exchanges of x and p. So this is the idea of what we're doing now about creating coherent states. And the basic idea of coherent states is that there are minimum uncertainty wave packets that populate phase space, parameterized by their expectation values of position and momentum. By the way, before I go further with coherent states, let me say that in current physics, I think there's two main uses for coherent states. One of them is really conceptual or theoretical. They're used for exploring the classical limit. The reason is that a coherent state has a minimum dispersions in x and p. We know because of the uncertainty principle that you can't make measurements of position and momentum with infinite precision simultaneously as you can in classical mechanics. However, a coherent state is as close as you can come to that, and so in some sense it's the quantum object, and some people think of it this way, it's a quantum object that is as close as possible to a single point of a definite classical state. And so they're used in all kinds of studies. Very common in the literature nowadays to use them for this purpose. It's used for studies trying to understand the classical limit of quantum theories. There's a second purpose of coherent states, which is in the case of quantum optics. They are quantum states that can actually be produced with lasers. And they're different than these energy eigenstates, which in the case of lasers are states of a definite number of photons. Coherent states have a variable number of photons. It's not an eigenstate of the number operator. But in any case, they're interesting experimentally for things that one can do with them. I'm mainly here going to concentrate on the use of them for understanding classical correspondence. All right. In any case, the main problem I want to address now is the non-commutativity of these operators S of A and S of T of B. Excuse me, S of B and T of A. In order to work around this, I'm going to define a new operator, which is called a Heisenberg operator. And it's just kind of a combination of translations and position and momentum taken at the same time. I'll call it W, and it's parameterized by both A and B. And this is defined to be e to the I times bx hat minus ap hat. So it looks like the t of a and the s of b with the exponents combined. That's all it is. However, this is not equal to e to the I bx hat times e to the minus I ap hat, which is the same thing as s of b times t of a. It's not equal to it because x and p don't commute. If x and p were ordinary numbers, which do commute, then the usual rules of exponentials would give you an equality here. These things would be equal. But because the ordering matters, this is actually not true. There's some other stuff that has to be taken into account. However, the Heisenberg operators can be expressed in terms of these s and t operators. It's not too complicated. And the way to get from one to the other is to use what is called Glauber's theorem, which I'll now tell you about. Glauber's theorem has rather restrictive conditions on it, so it's not applicable in many circumstances, but this happens to be one of them, and so it's useful for this. Glauber, by the way, is the physicist at Harvard who won the Nobel Prize for his work on quantum optics, which he did mainly in the 1960s. All right. It is all related to this kind of stuff. All right. Glauber's theorem says this, is that if you have two operators, A and B, which commute with their commutator, then there's a nice identity that says that e to the A times e to the B is equal to e to the A plus B. That's all you'd have if they commuted. But then there's an extra term, which is 1/2 the commutator of A with B. So in particular, if they do commute, the commutator is 0, and you just get the usual rules of exponentials. Let me go over here to prove this. I'll give you the proof. Let's define, this proof will follow what we did in the first homework problem, one of the first homework problems, first homework set. Let's define an operator that depends on a parameter lambda, which is equal to e to the lambda a times e to the lambda b. And we'll get a differential equation for it by differentiating. df to the lambda is equal to a times e to the lambda a times e to the lambda b plus e to the lambda a times b times b times e to the lambda b, like this. By the way, let's note that f of 0 is equal to the identity operator. It's kind of an initial condition for this differential equation we're going to get. Now in this line here for df d lambda, by the way, you see I brought these operators a and b down to the left when I did the differentiation. In this expression for this derivative, allow me to insert here between the b and e to the lambda b, let me put in e to the minus lambda a times e to the plus lambda a, which of course cancel out. And the reason for doing that is that we get on the right-hand side here in this term e to the lambda a, e to the lambda b, and likewise in this term e to the lambda a, e to the lambda b, the same term, and that's just the same thing as f itself. So effectively, we've factored out f to the right of this. And so this becomes this expression. It's a plus e to the lambda a times b times e to the minus lambda a, the whole thing multiplied onto f. So this is our differential equation. Now, at this point, we haven't made any assumptions about a and b. It's actually true for all a and b. But again, going back to that first homework exercise, this product here, which is exponentials conjugated around b, this can be developed into a power series of iterated commutators. In particular, it's equal to b plus the commutator of, here's multiplied by lambda, so it's lambda, the commutator of a with b, plus lambda squared over 2 factorial times the iterated commutator of a with the commutator of a with b, plus dot, 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 infinite series like this. And that's also always true. However, Glauber's theorem says we're going to assume that a and b commute with their commutator. In particular, that means that this lambda squared term goes to 0. In fact, all the higher order terms all go to 0. All the iterated commutators are 0. And so we're just left with the first two terms of this series. And so this gives us then, to rewrite the differential equation, as df of lambda is equal to a plus b plus lambda times the commutator of a with b times f of lambda. Now, if this differential equation were numbers instead of operators, it would be easy to solve. It would be that f of lambda would be equal to e to the lambda times a plus b plus lambda squared over 2 times the commutator of a with b. This is assuming f of 0 is equal to 1. But we have to put a question mark on this until we can check to see that this is true even for the case of non-commuting operators. Well, in fact, it will be true for non-commuting operators if the derivative of the exponent commutes with the exponent itself. The derivative of the exponent is a plus b plus lambda times the commutator of a with b. And you can see they do commute. A plus b, any operator commutes with itself. So a plus b commutes with a plus b. A plus b commutes with the commutator because that's what we're assuming. The commutator commutes with a plus b, and the commutator commutes with itself. So the derivative of the exponent commutes with the exponent, and so, in fact, the solution is correct. This works, and this is the solution for this function f of lambda. And now finally, all we need to do is just set lambda equals to 1, and it turns into the theorem which is stated over here. That's the proof of the theorem. All right, now, I don't care so much about the proof anymore. Let's erase it. Let's apply the theorem. Let's do this. Let's let A be equal to IB x hat, and let's let B be equal to minus IA p hat, using these products of these displacements in momentum and position. Then the commutator of A with B is equal to I times minus I is 1, lowercase a times lowercase b I'll write down. What's left is the commutator of x hat with p hat. But that's equal to I, since h bar is 1 here, so this just becomes IAB. The commutator of these two operators is a constant. It's a C number. The C numbers commute with everything, so in particular they commute with A and B, and so the conditions of Glauber's theorem are met. And the result is that this operator, e to the IB x hat times e to the minus IA p hat, is equal to e to the I b x hat minus a p hat combined together in the exponent plus I a b over 2. What's the result for the product of a momentum times a position displacement? You see it's a Heisenberg operator in the first term, defined up here, and then a correction term, which is a phase factor. In fact, since this is a phase factor, it commutes with everything, and I can just put it as e to the I as a separate phase factor here, and even bring it back over to the other side. And if we do this, then we get this result, is that the Heisenberg operator WAB is equal to S of B times T of A. Well, let me put the phase factor first. E to the minus IAB over 2 times S of B times T of A. And so this then allows us to express the Heisenberg operator in terms of position, momentum, displacements. All right. Now, having done that, let's now define a general coherent state, which is going to be parameterized by its expectation values, A and B. These are expectation values of position and momentum. This will be defined as the Heisenberg operator W of AB acting on the ground state. And if we work out the wave function of this, let's call it psi AB of x, which is equal to the scalar product of x with the state AB, like this. It's straightforward. We work this out by just applying position and momentum translations. You'll find that this is the same normalization whenever applied to the 1/4. E to the minus x minus a squared over 2, that's the x shift, did that. Then you get plus I dx, that's the momentum shift, and then minus IAB over 2, which is this extra phase factor here. And so this then is the wave function of a coherent state minimum uncertainty wave packet with given expectation values of x and p. Think of it as a blob in phase space. And by using the Heisenberg operators, it's symmetrically treated in position and momentum. That's where this extra phase came from. All right. Now, to go back to our original problem then, which will still be here back on this board, what we'd like to do to understand the classical limit is to take an initial condition for the quantum harmonic oscillator, which is a coherent state centered at some position x0 and p0. I've been calling this A and B, but now I'll call it x0 and p0 because we'll think of it as an initial point on a classical orbit, like this in the classical phase space. And then we'd like to do the time evolution in quantum mechanics. Maybe before I do that, let me say something about the time evolution in classical mechanics. Well, I already showed you what it is. It's just a rotation by an angle. But there's a convenient way of expressing this that I'd like to tell you about. That is to introduce complex coordinates in the classical phase space. Let's introduce a coordinate I'll call z, which is defined to be x plus ip over the square root of 2. So z is a complex number. And except for the square root of 2, this is really identifying the phase plane, the xp plane, with a complex plane, so it's the real and imaginary parts of z. The square root of 2 is just convenience here. You might notice, however, that this is a classical definition now, so the x's and p's are extraordinary numbers here. But you may notice that this is a classical formula, which is exactly the same as the definition of the annihilation operator in quantum mechanics. So the z is a classical analog of the annihilation operator. Likewise, let's introduce the complex conjugate of z, which is equal to x minus ip over the square root of 2. I'll denote the complex conjugate with a bar here. So that's like the A dagger. All right. Now, if we do this, then this x0, p0 can be translated into a complex initial condition, call it z0. And this x of t and p of t can be translated into a complex final position called z of t. And it's easy to see what the solution of the classical equations is. It's that z of t is equal to, it's just the phase factor, which is e to the minus it multiplying on the z of 0. In complex variables, the time evolution becomes really simple. By the way, I might mention that this is a classical analog of the solution of the Heisenberg equations of motion in quantum mechanics for the annihilation operator. If you solve those, what you find is that A of t is equal to e to the minus it times A of 0. This is in the Heisenberg picture. They're exactly the same formulas. No wonder the equations are exactly the same too, except for a reinterpretation of the symbols. All right, anyway, this is a useful way of talking about the classical solution in terms of these complex coordinates. Now, if I may go back to the, where do I have it? These Heisenberg operators, are they here? Allow me to make some further slight changes in notation. This is really pretty simple. Let's, first of all, let's take A and replace it by x0 and B and replace it by p0, because we're going to be thinking about these displacements as moving us to some initial condition. And then we've got a Heisenberg operator, which is parameterized by x0 and p0. And just as by way of notation, let's also write this as w of z0, where z0 is the complex coordinate x0 plus ip0 over the square root of 2. Just a different way of parameterizing the same operator. And similarly, as far as the coherent state itself is concerned, which I called AB over here, let's call x0 p0 is w of x0 p0 applied to the ground state 0. And let's also just define this to be Z0 for short. Again, parameterizing the coherent state also by the same complex numbers, complex coordinate in the phase space. So let's do that. Now then, here then is the problem that we'd like to solve. As we like to say, suppose the psi initial time 0 is equal to this initial coherent state. The problem is, what is the psi at later time t equal to? This is an initial value problem for the Schrödinger equation under the harmonic oscillator evolution. By the way, according to the Ehrenfest relations, which we went through before, the expectation values follow the classical motion. They do because the Hamiltonian is a quadratic function, the potential is a quadratic function. And so in particular, we know that whatever this solution is, the expectation values of x and p will follow this same classical orbit here. However, that still leaves open the question about whether the initial coherent state remains a coherent state. Does it remain a minimum uncertainty wave packet? Actually, the dispersions only involves the second moment. What we'd really like to do is to solve the Schrödinger equation and get the whole solution of the quantum problem. So it's actually more than just looking at expectation values. But at least we know something already about the solution from the from the Ehrenfest relations. All right, so anyway, to go back, then, this is going to be the problem we'd like to address. So the answer, of course, is that psi of t is the unitary time evolution operator u of t acting on this initial coherent state Z0. And this, of course, is the Hamiltonian e to the minus ith, really h hat, if I'm making an operator, acting on Z0. The strategy I'm going to use for solving this problem is to decompose the initial coherent state at location Z0 into a linear combination of harmonic oscillator eigenstates. And then we'll evolve that forward in time by the usual method of basically normal modes of time. So the first task is to take the initial coherent state and to decompose it into energy eigenstates. So here's what we've got. So we've got Z0 then is equal to the same thing as x0, p0, which is the same thing as W of x0, p0 acting on the ground state, which is the same thing as e to the I p0 x hat minus x0 p hat applied to the ground state. That's the Heisenberg operator. Now, allow me to do this. Let's go from the x0 and p0 are c numbers, ordinary numbers, and the x hat and p hat are operators. Let's express these in terms of their corresponding complexified versions. So the x hat is equal to a plus a dagger over the square root of 2. P hat is equal to a minus a dagger over I to the square root of 2. X0 is equal to z plus z bar over the square root of 2. This is a classical correspondent. And then we've got p0 is equal to z minus z bar over I to the square root of 2. This is just using defining relations to go over from x's and p's to a's and a daggers in the quantum operators, or z's and z bars in the classical picture. I should put knots on the z's here because they refer to the initial conditions x0 and p0. And if we do this, and you transform this exponent, you find it turns into this. It turns into e to the power of z0 times a dagger minus z0 bar times a applied to the ground state. It's just algebra to transform that exponent in these equations, and if you do, it turns into this. So this is what we need to evaluate now. For this purpose, I'm going to use Glauber's theorem again. Let's consider the product e to the z0 a dagger times e to the minus z0 bar times a. And let's let our first operator a be z0 a dagger. Capital A is z0 times annihilation operator a dagger. Capital B is equal to minus z0 bar times annihilation operator a. This is a good principle. So the result is the ground state of the harmonic oscillator is actually a minimum uncertainty wave packet. It's a Gaussian wave packet. All minimum uncertainty wave packets in terms of delta x and delta p have to be Gaussian, but this is a particular example of it. So that's an interesting conclusion also. While I'm talking about momentum, by the way, it's interesting to take the Fourier transform of psi 0 in order to obtain a momentum space wave function, phi 0 of p. That's straightforward. It leads to the same 1 over pi to the 1/4 normalization, and then it becomes e to the minus p squared over 2. The result is, as you see, that for the ground state anyway, the momentum space wave function has the same functional form as the configuration space wave function. This is an example of a wave function which goes into itself in a Fourier transform. All right. Now, so those are some basic facts about the ground state. Now, let's take a look at the excited states. Let's see, maybe before I do that, let me just provide some motivation for where we're going here. The harmonic oscillator is a particularly useful system for exploring and understanding the correspondence with classical mechanics, to understand how far it goes and what needs to be changed by going to quantum mechanics. It makes the relationship between the two particularly clear. And that's really going to be the main theme that we'll be following in the rest of the lecture today, is to understand the relation between classical and quantum mechanics. Here's just one thing to say, is that because this ground, let's shift attention now to the excited states, n. Say n is one of the excited states. And let's consider the expectation values of position and momentum for the excited states, just to see, because expectation values of position and momentum are ordinary numbers, and they could be, they sort of look like classical quantities. So let's consider the expectation value of position, let's say, in an energy eigenstate. Then I'll put a hat on the x to emphasize that that's an operator. Similarly, we can do this for the momentum. Look at the average value of momentum in an energy eigenstate. By the way, my use of the hats here is that I tend to put hats on something to indicate that it's an operator when there's some danger of confusion between the operator and something else like an eigenvalue or a classical quantity. And I tend not to do it when there's no danger of confusion. That's the rule for the hats for the time being. Well, in any case, these expectation values are easy to work out. The easiest way to do it is to write it in terms of A's and A daggers. And if you do that, you find quite easily that both these expectation values are 0. So, as far as expectation values are concerned, an energy eigenstate doesn't look at all like a classical particle in an orbit. If you have a classical harmonic oscillator and you give it some definite energy, it's going to swing back and forth with an amplitude. So the question is, where is that the classical time dependence in the quantum problem? It's not appearing here in energy eigenstates at all. In fact, energy eigenstates in quantum mechanics are what they call stationary states. That means the probability density in configuration space is independent of time. And so any expectation value you take of any operator is going to be independent of time in an energy eigenstate. Therefore, there is no time evolution at all. In particular, it states the harmonic oscillator has these dispersions. This is obviously related to the statistical nature of a quantum measurement. We can visualize the ground state of the harmonic oscillator in quasi-classical terms in the following way. If I plot the classical phase space x and p, then we can think of the ground state of the harmonic oscillator as a kind of blob or a distribution which is centered at the origin in phase space. It's centered at the origin because the expectation, the average values of x and p are 0. But on the other hand, it has some spread around it because of non-zero dispersions. Spread, of course, is necessary by quantum mechanics because x and p don't commute, and so they can't be measured simultaneously with infinite precision. This blob that I've drawn here is not intended to be a rigorous representation of the ground state. It's really intended just for intuition, purposes of intuition, to give you an idea. It represents in some way the statistics of measurement that come out of the ground state wave function. One could make this more precise by going to the Wigner function, which was actually a part of last week's homework problem, but I won't go into that. We'll just use this for illustrative purposes. All right. Anyway, that's what the ground state looks like. Now, in thinking about the classical limit of the harmonic oscillator, or for that matter, any quantum problem, hydrogen atom, one is struck by the fact that in classical mechanics you have particles moving on orbits. And in quantum mechanics, you've got these energy eigenfunctions. At least that's what people talk about most of the time. And an energy eigenfunction doesn't look at all like a particle moving in an orbit. And the question is why? What's the difference, and how do we understand this? Well, just for the case of the harmonic oscillator, x is equal to 0. It's a simple differential equation, and it's easy to solve. And if you solve it and if you normalize the result, you find that psi 0 of x is 1 over pi to the 1/4 power times e to the minus x squared over 2. The pi stuff is the normalization. And this is the ground state wave function, which is, I guess you know, is a Gaussian function, a function of x. It's a Gaussian function centered at the origin. That's the ground state of the harmonic oscillator, psi 0 of x, here like this. Now, one of the things we're going to be interested in paying a lot of attention to today is expectation values of position and momentum, as well as dispersions, which are like expectation values of first moments. We'll also be interested in second moments, which are related to the dispersions. And in particular, if we compute these for the ground state, it's easy to show that the expectation value of x and the expectation value of momentum p are both equal to 0. This is for the ground state. And one can also show quite easily that the dispersion delta x is equal to the dispersion also in momentum p, which is 1 over the square root of 2. This means, obviously, the dispersions are equal, and it also means that the product of delta x times delta x times delta p is equal to 1/2. This is all in units and where h bar is equal to 1. So this would be h bar over 2 in ordinary units. And this is the minimum value of delta x and delta p, which are allowed by the uncertainty. The main results of the presentation I gave the last lecture on the Dirac method for Dirac algebraic method for solving a hydrogen atom. My mind is elsewhere this morning. The Dirac algebraic method for solving a harmonic oscillator. I think you're probably familiar with most of this. The essential ingredients are the creation and annihilation operators. There are matrix elements with respect to the energy eigenstates. The expression of the Hamiltonian in terms of the creation and annihilation operators. We've also solved for the position and momentum in terms of the A's and A daggers, just the inversion of the definitions, which is also sometimes useful. All right. Now, I'd like to begin today with the subject of wave functions. In particular, let's talk about the ground state wave function. 0 is the ground state. And if I form the scalar product with the position eigencat x, we get what we consider to be the ground state wave function called psi 0 of x. And the question is, what is psi 0 of x? Well, this follows easily from the fact that the annihilation operator acting in the ground state annihilates. It just gives you 0. The annihilation operator, however, is x plus ip over square root of 2. And if we put that in the wave function language, x plus ip goes over into x, of course, is let's put hats in this and emphasize these are operators. X goes into multiplication by x, p goes into minus I ddx. So, excuse me. So as an operator, acting on the wave functions, this goes into x plus ddx. And therefore, the ground state wave function satisfies the differential equation that x plus ddx, acting on psi 0 of x,